Professor, I've started the recording. You're on mute, Professor.
Okay, great. So we'll give a minute or two for people to join in. Maybe at 11:01 we can start playing the video. Okay, after I do the introduction.
Sure, Professor.
Thank you. Okay, let's get started. Are we ready?
Yes, Professor.
Okay, so we are in the research track. It's research track 21, temporal and spatial track, the second track on temporal and spatial data. So we have 5 talks today. The first talk is by Jia on turbocharging geospatial visualization dashboards via a materialized sampling cubing approach. Jia is a PhD candidate in the Department of Computer Science at Arizona State. Jia's research focuses on large-scale database systems and geospatial data management. In particular, he's worked on distributed geospatial data management systems, database indexing, and geospatial data visualization. So we'll see his video first and then ask questions appropriately. Thanks.
Hello everyone, welcome here. Today I'm very glad to be here and talk about our paper. The title is Turbocharging Geospatial Visualization Dashboards via a Materialized Sampling Cube Approach. My name is Jia. This is the paper I collaborated with my advisor Mohammed Shawart. We are from Arizona State University. Okay, let's get started. You probably have heard of geospatial data, but you may not know geospatial data is actually very big. Geospatial data can come from your mobile devices, so many different apps on your cell phone can generate geospatial data. And big spatial data can also come from the LT sensors that include sensors installed on the bikes and the scooters. And it also come from climate monitoring services. You know, NASA has a number of spacecraft running outside the Earth to monitor status of the entire planet. So given the big spatial data, how can people make sense of data? Now let me show you how the entire spatial data science pipeline looks like. So we store the spatial data in spatial database systems such as Postgres, PostGIS, or distributed data systems such as Apache Spark and Hive. These systems support spatial queries and they can create database indices to speed up query processing. On top of that, we use analytics tools to do analytics on data, such as spatial visualization and spatial data mining. Analytics tool can be Google Maps, ArcGIS, QGIS, Tabula, Python, so many different analytics tools. So recently, among these tools, the interactive visualization dashboard such as Tabula, ArcGIS, and Apache Zeppelin become very popular. In this kind of interactive visualization dashboard, they usually include two panels: the analytics panel, which allows the user to draw visualization effect on selected data; the filter panels that includes a number of different filters. The user can select different population interactively by clicking different filters. So the analytics panels will visualize the selected data population immediately after each interaction. So as you can see here, this kind of interactive visualization dashboard requires the interactive analytics support from the underlying data systems. However, this visualization dashboard have some problems when they deal with big spatial data. This is because every interaction on the dashboard involves two steps. The first step is the database query step. After each interaction on the visualization dashboard, the dashboard will send SQL query to the underlying database systems. Running this query in the database systems will take several minutes to finish, even with the help of Apache Spark or Hive, and this time may increase with the datasets. After we get the query from the underlying database, the second step is to visualize the result in the visualization dashboard. If the returned query result is large, actually the visualization step will take a very long time to finish, or it may even crash. So if you can go back to use Tabula or Google Maps to draw heat map applications on the data. Actually, this kind of application will start at 100 MB. After that, it will take forever to finish, or it will just crash your computer. So how can we solve that? A very straightforward method is to use sampling techniques. The intuition behind that is, for this kind of visualization applications, people may tolerate some accuracy loss for the visualization. That means people may not even notice there are some slight difference between the actual visualization and the visualization people see on the visualization dashboard. So a very straightforward technique is about the sample first technique. The sample first technique means we just simply draw a sample on the entire dataset, and then we run the dashboard applications on this sample. So this is called sample first technique. This sample first technique, for sure, it will make the visualization dashboard more interactive. However, it will lead us to ignore some important patterns. As you can see from here, this sample first technique will lead us to ignore the patterns that are inside these red circles. In order to improve that, some people propose to use online sample. That means we still run database query on the entire dataset, but after each query, we draw a sample on the returned query result in an online fashion. So this is called sample on the fly technique. This sample on the fly technique, for sure, it will make the visualization fast and more accurate. However, the database query part is still running on the entire dataset, which is still very slow. How can we improve that? Some researchers and practitioners propose to use stratified sampling technique to solve a similar problem. So the idea behind that is they carefully create a stratified sample by considering different filter selections, such that they can make the returned aggregate values more accurate. The aggregate values include sum, average, and count. For example, you can think of different filter selection as a hypercube in the selection space, which is the hypercube on the right. So every filter selection on the visualization dashboard can be considered as a cube cell in this hypercube. This stratified sampling technique, they want to improve the accuracy of this kind of query. Each time it only returns a single aggregate value. However, if I bring back the visualization dashboard example we used before, so after each interaction, we actually require the sample for each interaction. We require the sample to draw the data distribution and draw the heat map. Therefore, the existing stratified sampling technique cannot be used in our scenario. This motivates us to propose our Tabula systems. Tabula is a sample middleware system that sits between the front-end visualization dashboard and the underlying SQL data systems to support interactive analytics on the visualization dashboard. The idea of Tabula is that it tries to materialize local samples for all future queries, which are all the cells in this hypercube. It returns a sample for every interaction on the visualization dashboard, it never goes back to the raw data in the online fashion. We call this approach as the Materialized sampling cube approach. Apparently, this Materialized sampling cube approach have a huge storage overhead and long construction time because there are too many cube cells in this hypercube. Later on, I will show you how can reduce the overhead of Tabula. Before I go into the technical details, let me briefly talk about the system design philosophy in Tabula. We want to design a sampling middleware system. That means we want to have a plug-and-play solution. There is no change to the front-end dashboard and it requires no change to the underlying data infrastructure. Also, we want to support a pluggable function for sample quality because we believe that domain experts know better about their own needs. And we also want to support a variety of different analytics applications on the visualization dashboard. This is an example. So now, let me talk about how can we reduce the storage overhead in Tabula. We first propose a technique called partially materialized sampling cube to reduce the storage overhead in Tabula. The idea behind that is actually very simple. We first draw a global sample on the entire dataset. We try to use this global sample whenever it is possible. We only draw local samples for low accuracy queries, which has red color cells in this hypercube. This partially materialized sampling cube can be represented by these SQL queries down there. So you may ask me, so what are the low accuracy queries? So the definition of the low accuracy query is that if we use the global sample as the query result, the produced visualization will exceed the user-specified accuracy loss threshold. For example, suppose we have the raw query result look like that one, which is similar to the global sample. That means I can use the global sample as the sample for this query. So this is a high accuracy query. It is good. However, if we have the raw query result look like that one, which is very different from the global sample, that means I cannot use the global sample as the sample for this query. So I say that this is a low accuracy query. This is bad. Okay, so we have reduced the storage overhead. Use the partially materialized sampling cube. The question is, can we do better? Can we reduce even more? The answer is yes. So in Tabula, we propose a technique called the sample selection technique to further reduce the storage overhead. The intuition behind that is some local samples, they look like each other. We can formulate this similarity problem as a graph problem. We call this graph as a sample representation graph. If sample 1 can represent sample 2, we draw an edge from sample 1 to sample 2. That means if I use sample 1 as a sample for query 2, the produced visualization will never exceed the user-specified threshold. The sample selection problem is that we want to select a minimum set of local samples to materialize and use them to represent all other local samples. This sample selection problem is very difficult. It is an inherent problem. Therefore, we develop a greedy algorithms to select the samples. In this example, given all these 8 local samples, only sample 2, 8, 5, and 4 are selected to materialize. And we have been talking about accuracy loss for a while. Now let me explain what is the accuracy loss function in Tabula. First of all, in Tabula, it allows user-defined accuracy loss threshold. That means Tabula can guarantee that the sample received by the dashboard never exceeds the user-specified accuracy loss threshold. In Tabula, we also support user-defined accuracy loss function because, like I said before, we believe the domain experts know better about their own needs. We also want to make sure our system can fit in different scenarios, such as heat map, linear regression, so on and so forth. Although Tabula allows user-defined accuracy loss function, we have a specific requirement to the function. So this accuracy loss function has to be an algebraic aggregate function. This feature will be leveraged later. So what is an algebraic aggregate? That means the value of this function can be computed by several functions in its subdomains. For example, we can count the number of trips paid by cash and count the number of trips paid by credit card. So the overall count of all trips will be the sum of two counts. So actually in practice, the algebraic aggregate functions are very common, such as we count, sum, average, min, max. They are all algebraic functions, and this algebraic feature will be beneficial to the cube initialization. So another important thing I want to talk about is the sampling function. So given the definition of the accuracy loss function, so the sampling function will be used to draw the local samples for low accuracy query, and it is generic for different user-defined accuracy loss function. It uses greedy algorithms to produce samples. It will produce samples that guarantee that the accuracy loss is smaller than the user-specified threshold. Also, this algorithm tries to minimize the sample size at the same time. Okay, now all the concepts are very clear and the storage overhead is reduced. However, we still need to reduce the construction time of the cube. This is because the naive construction method as specified in these SQL queries may take 2 to the power of the n of the full table group by queries, where n is the number of columns in this table. So this is grows, as you can see here, it grows exponentially with the number of attributes. In Tabula, we equip the more efficient algorithms to build this cube efficiently and quickly. We call these algorithms as the dry run algorithms. It has two stages. Dry run stage. In the dry run stage, it quickly detects low accuracy queries, which has the red color cells in this hypercube. In the second stage, which is the real run stage, it only runs a few group by queries when it is necessary to materialize local samples for low accuracy queries. Now it's time to see some performance. Here we build a heatmap application, heatmap dashboard on Apache Spark. We run the experiments, this dashboard application on 200 GB MSA text dataset, which has 5 columns involved in the visualization dashboard. We compare Tabula with sample first method, sample on the fly method, and POSM. This is about execution time, so the lower is better. As you can see here, the query time about Tabula is around 300 milliseconds, which is very fast. Here, we also show the execution time for some other applications in Tabula. We show the execution time for linear regression and the execution time for the average applications. As you can see from these two figures, so basically Tabula has its own execution time around 100 milliseconds up to 300 milliseconds in both applications. We also can see the accuracy loss for different systems here. So here we compare the accuracy loss for different systems. The accuracy loss for the sample first method is extremely bad, so we just omit it in this figure. So as you can see here, the accuracy loss of Tabula is guaranteed to be within the threshold. The accuracy loss of POSM sometimes may exceed the user-specified threshold. Okay, here is the takeaway of today. So what did you learn from my talk today? So Tabula is a sample middleware system for interactive visualization dashboard. It has interactive performance and it is a plug-and-play solution. It has deterministic accuracy loss guarantee for different query on the dashboard. It allows user-defined accuracy loss function with algebraic feature. It allows it has different algorithms to support low storage overhead and quick construction time of the cube. Okay, that's all today. Thank you.
Thanks, Sya. Any questions from the audience?
Yes, I have questions.
Yeah, go.
I would like to ask. I see that this is also based. You're also talking about how to speed up the cube map, or do you also consider for other types of heat map visualizations techniques, for example, using kernel density estimation to do the visualization?
So yeah, so we actually like I said, so in our approach, we allow user to support the user specified accuracy loss function. So what we do is that, what we ask from the user is that to provide us the accuracy loss function you want to use, and the middleware we provide, the Tabula middleware will provide you the sample data set, and then you can have your own visualization software to visualize the data in the way you like. You can do your heat map using your different dense function to have different visualization result. That is up to you.
Okay, thank you.
Yeah, thank you.
Okay, one question from Supriya Roy. He says that nice talk. Does your system deal with updates? If so, does it perform resampling?
So that's a very good question. So actually, our system does not support updates right now.
We have time for maybe one more question. Okay, so I have a very quick question. Can your aggregated accuracy loss, can it be over specific regions? Can I say that this particular region needs to have minimal loss? I'm okay to tolerate error on this side. Does your visualization tool allow such statements as well?
No, actually no. So okay. Our system takes a single accuracy loss function from the user, and it applies it everywhere in the systems. That's not okay. It cannot apply to a sub region.
Okay, thanks.
Yeah.
Thank you for a nice talk. So the next talk is by Ibrahim Sabek on Sya, enabling spatial awareness inside probabilistic knowledge-based construction. Ibrahim is a postdoc at MIT Database Group. He got his PhD and master's degrees from Department of Computer Science and Engineering, University of Minnesota in 2020 and 17 respectively. His research interests lie in the intersection area between systems and machine learning. He was awarded the University of Minnesota doctoral dissertation fellowship in 2019 for focus on scalable machine learning for big spatial data and applications. He also won the graduate student research competition of ACM 6 Spatial 2019 and was nominated for Best Paper Award of ACM's 6 Spatial 2018. So we'll see his video, and he's here to answer questions later. Anshul?
Hi everyone, this is Ibrahim Sabek, a postdoc at MIT. Today I'm going to share with you our system Sya for enabling spatial awareness inside probabilistic knowledge-based construction. This was part of my PhD work under the supervision of Professor Muhammad Moghul at University of Minnesota. So let's get started. As we all know that knowledge bases are everywhere. They have been used in so many applications like search engines, digital libraries, and other analytics applications. It's basically a process of extracting a set of structured facts out of unstructured data, like PDFs, images, text, and HTML web pages. For example, we can extract a knowledge base of spouses, as shown here in the example, using a set of knowledge base rules coming from domain experts. And of course, any of these entries in the knowledge base could have some errors due to the fact that we are relying on maybe noisy input and noisy rules. Therefore, probabilistic knowledge-based construction systems have been introduced where we can associate a probability with each entry in the knowledge base, and this probability represents the confidence that we have in this entry. For example, in Parag and Michel entry here, we are confident that their probability of being spouses is 0.85. Probabilistic knowledge-based systems have been there for a while, and so many systems are out there. Among of these systems, a recent and successful example is DeepDive, which is a very successful knowledge-based construction system in so many applications like fighting human trafficking, doing crime investigation, and also building other domain-specific knowledge bases. It has been recently acquired by Apple for $200 million. This shows how knowledge base is important in our life. And during the rest of this talk, we are going to use DeepDive as an example of the knowledge-based construction system. In general, all of these knowledge-based construction systems, including DeepDive, they have been specifically designed to deal with classical and typical data types like text, statistical data categorical. Meanwhile, we have spatial data for a long time now. So much data has been generated from different devices like cell phones, and also from different apps like Google Maps. Everyone now is using Google Maps for navigation. Also, beyond traffic data, we have so much data coming from medical field. For example, scientists used to model the brain data using spatial models, and also data coming from satellites in a raster format. So in all of this data sources, we have so much spatial data that can improve the performance of the output knowledge base. However, existing construction systems like DeepDive and others, they don't make full use of the spatial data that we have. They are just dealing with it as another data type and ignoring the main spatial properties like spatial data correlation between the data points during the extraction process. And this can lead to a subpar performance and inaccurate results in the extracted knowledge base. To validate our argument, we use DeepDive to build a knowledge base out of spatial data. In this example, we use it to build a knowledge base about Ebola infection rates in some counties in Liberia. And we wanted to see how the results will look like. Will there be some inaccurate results in the output knowledge base or not? In this case, we built a knowledge base for 4 counties. One of them, we know for sure that it has high infection rate as an evidence, and we wanted to infer the confidence scores of the other 3 counties. We also gathered some sanitation level information about these counties, and we used one simple inference rule that has 2 predicates. In this inference rule, we say that if there is a county X that has high Ebola infection rate and another county Y that has the same sanitation level as in X, then county Y itself should have high infection rate as well. We fed this inference rule along with the data to DeepDive, and we got these confidence scores for the missing 3 counties. As you can see, they are very similar, and we tried to compare them with the ground truth confidence scores that we have from the United Nations. Basically, in this ground truth, we have one confidence range for each county. And ideally, we wanted to have these inferred scores to be around the median of this ground truth confidence scores. As you can see, 2 of these counties are out of the range of the ground truth. The problem here that this is a spatial phenomenon. And as you can see from the figure here, that although Margibi is closer to Monteserrado than Gabropolo, its confidence score is lower than the one that we got in Gabropolo. And this is counterintuitive because this is a spatial phenomenon. The closer counties they are, the higher infection rate should be. Now we wanted to resolve this situation. We added another predicate that enforced the spatial semantics based on the distance threshold between the counties. Basically, here we say that if 2 counties are within a certain threshold, which is 150 miles, then Y should have high infection rate. We got new confidence scores, and they look more accurate than the previous ones. However, if you look at the last one here, its confidence score dropped almost to 0. And the problem here is that in DeepDive, they are dealing with these predicates as a binary predicate, which is not the case in the spatial world. We need to have a gradual semantic. If you look at the figure, Gabropolo is almost like close to the 150 miles. So it doesn't have to be like 0. It should be something very close to the range of the 150 miles. And to resolve this situation again, we wanted to support the inference rule with some step function predicates. And these step function predicates, we had like 100 predicate. Each one of them will be focusing on a certain distance threshold and will be contributing to the confidence score in a certain way. Now, when we fit this inference rule with the step function rules to DeepDive, we got much more accurate results. However, the execution time explodes because now instead of having one inference rule with 4 predicates as in the previous 2 rounds, we now have like almost 100 predicates. Now, what we want to ideally have here is that to have one predicate only with the gradual semantic, like the closer X and Y, the higher Y infection rate. and this cannot be supported in DeepDive. So to conclude here, what's the problem in DeepDive? Basically, it's built on top of Markov logic network, and this Markov logic network is designed for binary logic only, like bitwise and an OR. And it doesn't support any spatial semantics or gradual semantics, as we wanted in the B3 predicate. So if we have a spatial variation of Markov logic network that's efficient for understanding the spatial semantics, then we can build a knowledge-based construction system on top of it, and our problem should be solved. And that's exactly what we propose in Sya. We provide this framework on top of an efficient spatial variation framework of Markov logic network. We implemented our framework and then tried it with a core of DeepDive to show the effectiveness of the spatial semantics inside the knowledge bases, as we're going to see the details later. But before we go through the details, a little bit introduction about Markov logic networks. It's an efficient statistical learning and inference framework proposed by Pedro Domingos from University of Washington. And basically, it's very user-friendly, as shown here in the example. It's using first-order logical rules with simple weights associated with these rules to express the semantic of the problem. So this means that the user can only write the problems using a few rules like this, and no need for thousands of lines of machine learning code. And recently, this Markov logic network applications have been scaled up and become very efficient in memory processing. So this is like the DeepDive architectures that we have on top of Markov logic network. And basically it consists of 4 main modules: the language module, grounding module, learning module, and inference module. Basically, any application developer can write its application as a set of rules, as we mentioned before, and then we pass it to the language module to compile these rules, and then we pass it to the grounding phase, which constructs a graphical representation of these rules. This graphical representation will be associated with the weights of this rule. If there are some missing weights, we pass this factor graph to the learning module to learn these weights. After that, the factor graph should be complete, and then we pass it to the inference module, which is responsible for inferring the confidence scores of the knowledge base instances. And what we do in Sya, we keep the same Markov logic network architecture used inside DeepDive. However, we added our spatial awareness inside each one of these modules. We're gonna talk about these details later in each one of these components. Now, going back to the same examples that we started for the Ebola knowledge base, Sya can support this B3 predicate. And by doing this, we achieve more accurate confidence scores and keeping the execution time efficient because we don't have to execute so many predicates. And when we applied this with Sya, we got, as you can see here, much more representative confidence scores that compared to the ground truths that we have. Now we go back to the details, each one of these components. For the language module, instead of like developing a new language, we extended the DDLook language in DeepDive with some spatial functionalities. This is like an example of the knowledge-based rules used in the Ebola example. As you can see here, we highlight in bold the extensions, spatial extensions that we have. We can add spatial data types, we can add spatial functions, and also some spatial parameters that direct the Markov logic network to use, for example, exponential weighting function for the gradual semantic during the inference and learning module. Also in the grounding phase, once we have this spatial aware rules, we want to build the factor graph, and to introduce the spatial correlation between data types, we had to have a new spatial factor type that considers the spatial correlations over the variables based on their distance. This is an example for a spatial correlation based on the distance-based weight. And we extended this for the categorical case. And once we have all of these spatial factors created, we combine them in one factor graph along with the logical factors that we have from the original Markov logic network. To efficiently generate this spatial factor graph, we translate the rules that have spatial extensions into some spatial SQL rules. Here is the example that we have for the inference rule. It has like two predicates, which is within and distance, and they are translated into two spatial queries, two nested queries, like range query and spatial join. We also optimize the orders of these queries using a heuristic query optimizer and remove any unnecessary spatial factors generated using some heuristic approaches. The details of these approaches and optimizations are in the paper. And now we pass the factor graph to the inference module, which is the main component in the knowledge base because it's used to infer the confidence scores. In DeepDive, they are using vanilla Gibbs sampling algorithm, which is specifically designed for sequential and independent variables. Now, these variables will incur some slow convergence when we have some spatial correlations between them, because Gibbs sampling algorithms are not efficient in this case. So instead of this, we have a spatial variation of Gibbs sampling algorithm that's based on the conflict-based sampling. And to do this, we create in-memory spatial factor graph index, and then we partition the cells into non-neighbor cells, and then combine them into a set of conflicts. After that, we do the parallel Gibbs sampling in each one of these conflicts. The details of this algorithm also in the paper. And eventually, we have the learning module, which is used for learning the missing weights. And we provide the spatial variation of gradient descent optimization of this module based on the inverse weight method. And to guarantee the best performance, we applied a parallel technique for high throughput. For the experimental setup, we evaluated our knowledge base construction system Sya using two knowledge bases. And we reported both F1 score and total time for scalability. And we compared our system with DeepDive, the vanilla DeepDive. As you can see here from the overall performance, we can achieve almost 2 times accuracy over DeepDive and a little bit performance gain in terms of scalability. And also for the inference, we can achieve also faster conversions for the spatial Gibbs sampling approach compared to the vanilla Gibbs sampling used inside DeepDive. So in general, we conclude here that we motivated for the importance of knowledge-based construction. We see that the spatial data now is underestimated in terms of exploiting them inside knowledge-based construction systems. And we provided here an example that motivates our case. And then we gave the details of our system architecture. And then we provided, using experimental evaluation, the importance of the proposed approach. And if you have any questions, please feel free to send me over my email. Okay. Thank you so much.
Thank you for a nice talk, Ibrahim. Any questions from the audience? We have time for a couple of questions.
Hello, can I ask a question?
Yes, please.
Yeah, I have, my question is about, I'm not very familiar with this Markov logic model, but as it looks, they are extracting knowledge from the data. Right now, the graph, knowledge graph is very popular. Do you know the relationship between this model and knowledge graph of this MLN with knowledge graph? Thank you.
Yeah, so, okay, so basically Markov logic network is not a knowledge graph approach. In Markov logic network, it's a general framework for statistical learning and inference. And in DeepDive, for example, they are using it to model the knowledge-based case study. So basically, you can build any application using Markov logic network, not like knowledge-based only. And we can say that here in Markov logic network, it could be similar to the knowledge graph, that it constructs something called factor graph. And as we have shown, we have another variation called spatial factor graph. And this spatial factor graph, we are relating the constructed knowledge-based relations in a way that we can do some learning and inference on top of these variables in the later stages. So it's basically, as a short answer, it's not like similar to the knowledge graph. It's a very generic framework, and we use it to build a knowledge-based construction.
Okay, thank you.
Okay, so I have a question. I work in statistical relational learning myself. That's my main field. Justify, we even wrote a book on that very recently. So MLN is not the only way to do this.
Yeah.
Okay? Problog and PSL, and that allows for bigger things. And more importantly, the way DeepDive is doing is you have to write every rule by yourself. You have to write even the parameters inside the rule. You have to write the 150. If you don't write the 150, you're not going to get the results correctly. So my question to you is, how much of engineering that did you have to do to get the right results, right? Because 150, if putting between 150 and 175, I'm assuming can change a lot. Between 75 and 150 can change a lot, even that distance that you looked at. So how much of this did you do by yourself, A? And B, for instance, there are a bunch of learning algorithms based on gradient boosting that people, including our lab, have done, where we learn these parameters automatically inside the rules of these learning systems. KU Leuven has done some work on the Problock system for doing something similar. So have you looked at those systems for maybe augmenting the rules with some learning as well?
Yeah. So for the first part of your question, yeah, of course, it's a rule-based construction system, specifically in DeepDive. You have to have some specific rules from the domain expert. But for example, in the case of the 150 rules, you don't need to write these rules by yourself. You can like automate this through a program or something. You can write script to generate these rules. So basically, you can write these rules as much as you can.
But you still have to write the 150, right?
Yeah.
That's my point. That is all.
Yeah, exactly. That's why we avoided this. That's what we found that it's a problem in the current version of the DeepDive. Like to have this spatial support in an accurate way, we need to write this 150. What we have done instead of this, we have like one predicate only, and we try to support the spatial semantic inside the learning and inference approaches themselves, not like from the way that you express it using the rules from the user end. And for the parameters here, yeah, of course, yeah, we need to learn the main powerful thing about the DeepDive approach, or like the Markov logic network thing in general, that they are saying that if you don't have like specific initial weights for these rules, you can train them from like using some semi-supervised approach from the training data that you have. And of course, even if you do this using the vanilla Markov logic network, you find that it's still not optimal for the spatial aspect. We needed to adjust some equations like the gradient descent optimizer that they have inside the learning module. And we added some spatial variations to it. Of course, there may be like other methods to do this in a better job, but we just wanted to have a proof of concept for like tweaking any kind of this objective functions in the optimization process using spatial extensions can improve the performance substantially in the case of having some spatial relation. So our focus here is not like focusing on how to do the learning in a better way compared to like doing this like relative performance again if you have some spatial understanding inside the learning engine.
Okay, great. Thank you. Thank you. Really nice talk.
Yeah.
So thanks again. We'll move to the third talk. It's by Laley on fast query decomposition for batch shortest path processing in road networks. Dr. Laley is a postdoctoral research fellow at the Data Science Group, University of Queensland, Australia. His research interests include spatio-temporal data management, graph, and distribution computing.
Hello everyone, I'm Laley from University of Queensland, Australia. This topic is fast query decomposition for batch shortest path processing in road network. The shortest path query is widely used nowadays. Basically, given a graph G, we want to find the shortest path or the farthest path from between 2 points. Okay, and the problem here now is there's just a large amount of them during a very short time. So it's like we have 10,000 shortest path query comes in 1 second or even 1 million during the peak hour. And this large amount of shortest path queries, they come from the LBS services, taxi scheduling, carpooling, all these new emerging applications. So the scalability of query answering becomes a very severe problem in industry. Actually, we got this problem from the industry car operators. And one solution to cope with this is we add more servers, but really this is very inefficient in the resources. Another way to answer the to deal with it is to use some pre-computed indexes like CH, 2-hop, and path oracles. They are very fast for answering the shortest path, but they only work in a static environment. The neural network in real life is actually dynamic because when the traffic condition changes, the travel time changes. So in the graph, it's just your edge weight changes. So depending on how the edge weight changes, we classify the shortest path problem into these categories. First one is when the edge does not change, it's a static, we have shortest path, or if the edge changes is predictable, okay? If the edge change is predictable and the edge changes are just discrete, like a timetable, we have timetable for this path, or if the edge changes as a function is continuous, we call it time dependent for this path. Well, for the predictable ones, there is a unchanged, there is a stable timetable and a stable function there. So essentially, these predictable problems are still static path problem. What we are trying to do is work in the unpredictable version, right? A traffic accident happens, it happens. A traffic jam happens, it happens. It's not predictable. So we call it dynamic path. And we view this dynamic graph as a series of time snapshots at different timestamps. We only deal with the current ones. For the future one, there is another snapshot of the static graph, but we just don't know it. When we encounter it, we deal with it. One problem of using the index approaches in the dynamic environment is they need to maintain their index. Okay, for CH, it takes 10 minutes to construct. For 2-hop, it takes hours. And for path oracle, it takes even longer time to construct the index. Although they are very fast, but they cannot work in the dynamic environment naturally. And for the index-free approaches like the Jackstraw or A-star, these approaches, they do not need any indexes. So no pre-computation. When the network changes, they can run on it directly. So they may be slow for query answering, but they can adapt to the dynamic environment naturally. So how about answering a large amount of queries with this kind of index-free approaches in batch? And this is the aim of this work. The first related work that using this shared computation idea utilize a phenomenon called path coherence. Basically, it means the subpath of a shortest path is also a shortest path. That's an example here from S2T. There are many passes, but a large amount of them share the same path, right? The long blue ones. And the first work used this kind of path coherence is Global Cache. It's a 2012 schema paper, and basically builds a cache of shortest passes globally from the query log. But the problem of it is it's static. It has no refreshment or update, and all the cache is there, and it cannot change it. So what we want to do, we try to increase the hit ratio by adapting to the dynamic environment. And basically we build the cache for each local regions, and we decompose the queries according to these regions such that this query can share more subpasses. And we also reorder the query orders to make the best of the cache. Another idea here is region-to-region shared computation. So for a bunch of queries whose starting nodes are near to each other and the destinations are also near to each other, so we can just compute one shortest path between these two regions and also connect these sources to the one end of this long path and connect your destination to the other end of your long path. Well, the problem is this kind of works, they do not have any bound here. So what we try to do, we provide an error bound for this kind of method. The third stream of approaches generalize A-star, because in A-star, if all the queries have the same starting node, you can get a shortest path from all of them in just one run. And given a bunch of queries, we can decompose them in several 1 to n queries and several n to 1 queries. So we can answer them in a zigzag way. right? And for one-to-n query sets, we can decompose the destinations into different clusters and answer them in the different petals here. So one A star for one n to 1 to n, and one A star for n to 1. That's exactly. Here is a framework of this work. We have a large amount of query set, and we propose 3 batch query decomposition methods to decompose this large query set into several small subsets, and then we feed these smaller subsets into some batch algorithms. In this case, we have 2 of them, and get the results. So the problem we identify here is how to decompose this large query set into smaller sets such that they can share the computation as much as possible. So in other words, how to reduce the cost to answer them as much as possible. Here is an outline of our approach. On the left-hand side are the query decomposition methods, and the right-hand side are the query answering algorithms. We categorize the queries depends on their length. So for the medium length queries, we propose 2 methods, Zigzag and search space estimation. And these 2 methods just cluster the queries into different clusters in the shape of clouds. And for each of these clouds, we build a local cache to answer them in batch. For the long queries, we propose this Coherence-Aware co-clustering method, basically create a set of query subsets in the shape of dumbbells. For each end of the dumbbell is a query region, and for the stick of the dumbbell is that's one single long shortest path. And to answer them, we propose this for approximate region to region batch query answering with error bound. The first decomposition method is Zigzag. Actually, it comes from our very early work. We can decompose the query set into several 1 to n and n to 1 query sets, like example shows here. Then we merge these Zigzag 1 to n and n to 1 query sets in a Zigzag way. For example, we have several sets here, but we can cluster them into 3, like T1, S1 to T1, and we can go back from T1 to S2, and we can also then we add S2 to T2. So these 3 queries actually they come into 1 cluster, and we just need some angle threshold to help us do this. Similarly for S3 to T3, T4, and from T4 back to S4. The second decomposition method is called search space estimation. It's based on the idea that search space of the A star. Say, for example, for the 3 plots on below here, if the query direction is 45 degrees from the row directions, while the search space is an ellipse. But if the search query direction is same as the row direction, the search space of A star is basically a line. So we can use this angle difference to help us estimate the search space during one single search. So we first need to capture the row direction information. Basically, we just divide the road into hierarchical adaptive grids in the like quadtree and summarize the row directions of each grid hierarchically. Then we just compute the angle difference between your query directions and the row network, the portion of row network covers that directions. We have an angle difference, and we also have 2 points. So just basically math for us to determine an ellipse. And for the regions covered by this ellipse, we say these are the search space of this A star search. So this method basically visits the queries from the largest one and draw a big ellipse and put all the queries that it covers with similar directions into it, and we use them as the same batch. The third decomposition method is coherence-aware co-clustering. Basically, we want for a pair of U to V, we want to use a distance from U to U prime and U prime to V prime and V prime to V, these 3 segments to approximate the actual distance from U to V. Here are some maths just based on the well-separated pair decomposition, and here's just some proof of it. But that bound is not what we want. We want to use it reversely. We want to give an error bound, and how about we know the distance between U star and V star? We can actually know the region size around the U star and around the V star, such that all the points within this radius are bounded by this error bound eta. So given an error eta and distance u star between u star and v star, we know that the radius is smaller, should be smaller than eta times your approximate distance divided by 4 plus 2 times eta. Now with this, we can draw two smaller regions. But remember, we're still at a decomposition. The distance between u star and v star is not known at this stage. So we use 1.2 times this distance, times the heuristic distance to estimate the distance between u star and v star. So we just have some candidates at this stage. During the actual query answering, we'll do the refine. The first query answering method is the local cache. Basically, for each decomposed subset, we create a patch cache. Okay, for the patch cache, it just first we have a path list, and then we also build an inverted list from vertex to the passes. And during the query answering, if a path is found in the cache, we can answer it directly. Otherwise, we just insert it into the cache. The second query answering method, region to region, is just a refine of the previous co-clustering decomposition results. But this time we can prove that we can use 2 times of the R star as error bound radius. The details refers to the paper, and we just use from U to U star and U star to V star and V star to V to approximate the actual distance. We conduct our experiment on the Beijing row network. It has 300,000 intersections and 400,000 rows. Or if you view all the rows as directed edges, we actually have 600,000 rows. For the query set, we converted from 12 million Beijing taxi trajectories, which collected from over a month of collections. And we select these trajectories, view them as OD pairs randomly into query sets of 10,000, 100,000, 500,000, and 1 million. And for the cache set test, we use those OD pairs that are shorter than 50 kilometers. And for region to region test, we use all those OD pairs that distance between 30 kilometers and 80 kilometers. Here are the decomposition time of our 3 decomposition methods. For the co-clustering method, it's really fast. Even query set is 1 million, it's still under 1 second to process them. Search space is lower and the zigzag is lowest. When the query set size is under 100,000, all of these 3 methods can process them under 1 second. Here's a comparison between of the cache hit ratios. The higher the hit ratios, the better. Well, the blue one is the global cache of the Sigma paper, and the best one in this experiment is our search space estimation method. Here is cache size influence on the hit ratio. Basically, the larger cache size, the higher hit ratio. And this is query processing time. The search space method is the fastest among them all. And this is a query processing time in terms of the cache size. Basically, still the larger cache size, the higher hit ratio, and the faster query answering time. And this is the query processing time of the region to region method. It is way faster than the other comparison method. And we set our error bound as 5%, and as proof in this table, all the errors, maximum error are bounded by this 5%, and the actual error is just around 1%. This is a set of experiment in the multi-thread test. All the time actually in log seconds. Still the region to region is the fastest. And on the right-hand side are the 2 index methods. These are the index construction time. And we showed them here just to demonstrate our methods can work in the dynamic environment, while the index-based methods, well, they need time to reconstruct. In conclusion, this paper will work on the shortest path query decomposition problem, and we just propose batch shortest path algorithm in dynamic environment. So first we have 3 fast shortest path query decomposition methods. The first one, Zigzag, that takes advantage of one-to-one decomposition result. The second one, search space estimation, that can decompose the query set based on the search space estimation very fast. And third one, the Coherence-Aware co-clustering, that decompose the queries with error bound. Then we propose 2 batch query answering methods. The first one, local cache, it has higher hit ratio than the global cache, and also the error bound region to region approximation method. that is really fast and robust for very long-range batch query. In the general extension of this work, we'll also cope with the scenario of query streams and also how to update the cache. Okay, thank you.
Thank you for the nice talk. I don't think Lele is here. If I'm wrong, please correct me now. So yeah, if you have questions, Simon, you should probably email Lele and ask him for the feedback. Okay, thanks. So we'll move on to the fourth talk. It's by Shin Kao. Shin Kao, you're here, right?
Yeah, I'm here.
Okay. Thank you. It's 3 a.m. for you, so thank you for being here.
Yeah,
so
it's early.
His talk is on efficient attribute co-constrained co-located community search.
The title of our work is Efficient Attribute Constrained Co-located Community Search. This is a joint work between USTC, USW, SIAT, Baidu, and Aalborg University. I'm the presenter, Xin Cao. I'm a senior lecturer from USW. This is the outline of my talk. First, I will give an introduction to our work. Next, I will explain the problem definition. Then, I will present algorithms proposed. Following that, I will show some experimental results. And finally, I will conclude our work. Our problem is defined over attribute graphs, which can be used to model various networks, such as collaboration networks and social networks. For example, in DBRP, which is a collaboration network, each node represents author, and edges represent causal relationships between authors. And each author has an institute, which is a location. In Twitter, each node represents user, and edges represent their social relationships. And there are various attributes available in such networks. For example, the spatial locations, as shown in this DBRP example, and keywords information, such as text or tweets in Twitter. Community search is one of the most important tasks in network data analytics. People use various metrics to measure the structural cohesiveness of our communities. For example, key-call, key-click, and key-trust, etc. In our work, we use key-call, so I will show an example of key-call. And given a graph G, the key-call is a maximal subgraph where each node has at least k neighbors, which means that the minimum degree in subgraph is k. So for example, in this figure, A, B, C, D, the four nodes form a 3-call because in this induced subgraph, each node has 3 neighbors. And many attributes are considered in community search as well. For example, in work 3 and 4, the spatial locations are considered in community search. And in work 5, they aim to find the community such that their nodes share the most common keywords. We propose a problem of finding attribute-constrained co-located communities in attributed networks. These communities have the following features. First, structural cohesiveness. Vertices in the community are densely connected. Second, spatial collocation. The vertices in the community are close to each other. Third, attribute constraint. A given set of attributes are covered by the attributes associated with the vertices in the community. Existing studies ignore either spatial or attribute information during community search, and that's why we propose this problem. Our SLC search problem is formally defined like this. Given an undirected attributed network G, a query attribute set T, and a positive integer K, SLC returns the smallest subgraph G prime, satisfying the following constraints. A, connectivity. G prime is connected. B, attribute constraint. All attributes in T are covered by the vertices in G prime. C, structure cohesiveness. The minimum degree of G prime is no less than K, which is a key-call model. D, spatial collocation. The diameter of G prime is minimized. The diameter is measured by the maximum distance between any pair of vertices in the subgraph G prime. For example, assume we are given a collaboration network with 10 users. The keywords represent their expertise. In the query, we have the following keywords: machine learning, database, distributed system, and the value of k is 3. ACOC is formed by the nodes V0 to V4. Because the 5 nodes form a 3-core, their keywords cover all the given query keywords, and their locations are close to each other. How to find ACOC is challenging. As shown in the paper, the problem of ACOC search is NP-hard. The major issue is that in order to compute the smallest diameter, we have to enumerate the combinations of vertices, which renders the problem NP-hard. And therefore, we propose approximate algorithms for this problem. Before presenting the details, I introduce the following important definitions. First, the feasible community. Given a community GK and an attribute set T, we say that GK is a feasible community if all attributes in T are covered by GK. We also call it a T community. Next is the smallest feasible community enclosing square. Given a graph G and a set of attributes T, the smallest feasible community enclosing square is a square with a minimum side length enclosing a T community. SFCS has a ratio for the root square of 2 for the ACOC problem. However, the exact algorithm for SFCS search still has a very high complexity. In order to find SFCS faster, we propose the graded attributes cover algorithm, which has a 2 approximation ratio for finding SFCS. And thus, the approximation ratio for finding ACOC is 2 times the square root of 2. The steps are as below. First, we find the most infrequent attribute T and F among all given attributes. Next, for each node V and F containing T and F, we find the smallest square, which is centered at V and F and contains the T community. We adopt binary search for this step. Third, after all the vertices containing T and F are processed, we select the smallest square, and the T community inside this square is the solution of GAC. The large ratio of GAC is because it fixes a vertex V and F at the center of a square, but actually, such a vertex can appear at any position of a square. In order to gain better accuracy, we propose grid-based algorithms which can achieve an approximation ratio of 1 plus epsilon for finding SFCS, where epsilon is an arbitrarily small positive value. So the ratio for finding ACOC is a square root of 2 times 1 plus epsilon. So the framework of grid-based algorithms is as below. We first run GAC to get a square with side length phi. And because SAC has an approximation ratio of 2, so the search area must be a square centered at each V and F with side length 2 phi. Assume V0 is 1 V and F, and then the square is a search area around V0. Next, we split the search area into 2m times 2m grid cells, and then we check if a T community can be formed in a square covering S times S cells. The value range of S is from 1 to m. And finally, we return the square containing a T community with the smallest S as a result. For example, this red square could be the result if K is set to 2. It can be seen that the key step of this approach is how to find the smallest S. We adopt binary search for this as well, and we call a square covering S times S cells a filter. To check if a T community can be enclosed in a square covering S times S cells, we design 2 approaches, linear scan grade and binary scan grade. Consequently, 3 algorithms are obtained. GRID grade using linear scan grade, and the second algorithm BiGrade using binary scan grade, and the last one grade plus, which combines linear scan grade and binary scan grade. The final algorithm is based on the following lemma. Given the filter with n times n grid cells, if n is larger or equal to 10, we use binary scan grade, and otherwise, we adopt linear scan grade because it has better performance. The idea of a linear scan grade used in algorithm grade is very simple. We move the filter in the search area linearly and perform the check of a T community at each position of the filter. As shown in this example, we move the filter from top to bottom, and then move the filter to the right for 1 column and move from top to bottom as well. The idea of a binary scan grade in BiGrade is that we use binary search to find the row such that from the top of the current filter to this row, a T community is first matched. For example, assume that we are trying to check if a T community can be enclosed by a square covering 3 times 3 cells. So in linear scan grid, we will first check this filter, and it does not contain a T community. So we move the filter down by row and to this position, and the feasible community is found. And in binary scan grid, so we first use binary search to find this row, because from the top of the filter to this row, a T community is first met. And next, we move the bottom of the filter to this row, and we do a check, and we find a community in this square, which means that S can be further decreased. So we move to the next step by setting S to 2. And similarly, we use binary search to find this row, because from the top of the filter to this row, T community is firstly enclosed. And then we move the filter to this position, and we find the T community, and we return it as a result. So the final result is in this square covering 2 times 2 cells, and nodes V0, V2, and V3 form the community which will be returned. In the experiments, we compare the following algorithms. 2 baselines APA and APP-Fast are adapted from 2 algorithms of existing work. The original algorithms cannot be used to solve our ACOC search problem, and we adapt them to our problem. And we proposed 4 approximation algorithms: GAC, grade, bigrade, and grade plus. We conduct our experiments on 3 real datasets and 2 synthetic datasets. There are 3 parameters used in our algorithm, and we test their performance. So M is the number of grid cells used in grid-based algorithms, and K is the minimum degree, and T is a query attribute set. The 2 parameters are specified by users. The first experiment is to check how the number of grid cells M affects the runtime and accuracy of the grid-based algorithms. We do experiments on both real and synthetic datasets. We can see that Grid Plus always has the best efficiency. It is because it combines linear scan grid and binary scan grid. In terms of runtime, we can see that as the number of grid cells increases, all 3 algorithms run slower. This is easy to understand because when there are more cells, in binary search, we need to do more check to find the smallest square that can enclose the T community. And in terms of accuracy, the 3 algorithms have the same results, so they have the same accuracy. And we can see that the diameter of communities detected by the algorithms become smaller as the number of grid cells increases, and which means that they have better accuracy. The reason is that the gap between the exact smallest square that can enclose the T community and the approximate square found by the algorithms is only 1 cell. With a larger M, and the grid has a smaller granularity, and the cell size is smaller. So the gap between the approximate result and the accurate result is smaller as well. The second experiment is to check how the value of K affects the accuracy and the efficiency of the proposed algorithms. We only show the results on a synthetic dataset, Goala SYN here. And because an exact algorithm is not feasible on such a large dataset, so we are not able to show the absolute efficiency, absolute accuracy. And instead, we show the relative accuracy between our algorithms and 2 baselines. We divide the diameter of communities obtained by our algorithms by the diameter of the communities detected by the 2 baselines, and then we obtain the relative ratio. It can be seen that the ratio is around 1.1, which means that the result detected by our algorithms is very similar to the communities detected by the 2 baselines. And however, let's look at the runtime. And we can see that our 2 algorithms are faster than 2 baselines by at least 1 order of magnitude. And we can also observe that as the value of K increases, all algorithms runs faster. This is because we only consider nodes with degree larger or equal to K. So with a larger K, And before we start the search, mock nodes are pruned from the graph, so the algorithm is much faster. The third experiment studies the effects of the number of query attributes. It shows the results on two small real datasets, Flickr and Yelp. And we observed similar results as we do in the experiment of variant K. So our algorithms have slightly worse accuracy. However, our algorithms are faster than 2-bit lines by almost 1 order of magnitude. It can also be observed that as the number of attributes increases, the runtime is a bit longer. It is because that we should do more check for the key community because more keywords are involved. In summary, our work has the following contributions. We propose a COC search problem, which is shown to be NP-hard. We propose a concept called smallest feasible community including square to approximate the SOC search problem. Based on SFCS, we developed 4 efficient approximate algorithms for the SOC problem. We also report on extensive experiments on both synthetic and real-world datasets.
Thank you. Any questions for Shinkal? Very nice talk. I just have one quick question, Shinkal. Can you hear me?
Yeah, I can hear you.
So I was, I can see the effect of K. Is there any effect of the data size? Like the synthetic data sets seem to be significantly larger than the real data sets. Do you think they had, so what is the effect of the size of the data set on the performance?
It was in the paper. So because of the time limit of this presentation, I did not include that results in this slides. So we also vary the dataset size in the experiments. So we showed that our algorithm increase, the runtime of our algorithms increase linearly with the size of dataset, and it's faster than 2-bit lines by more than 1 order of magnitude. That's you can see more details in the paper.
Okay, great. Yeah, thank you. It was a really nice talk. Thank you.
Okay, thank you.
And thanks for staying up so late. So the final talk of this session is also by somebody who is staying up late, Feng Jijin. Jijin Feng received the BSc degree from Hong Kong Baptist University in 2019. He's currently a PhD student at the Department of Systems Engineering and Engineering Management, Chinese University of Hong Kong. His research interests include graph query processing, graph data management, and location-based services. And he's going to talk about indoor top K keyword-aware routing query. So let's play the video.
Hi, my name is Feng Jijin, and I'm a current year 1 PhD student from the Chinese University of Hong Kong. I'm going to talk about our paper, Indoor Top K Keyword-Aware Routing Query. And today's video will cover the following 6 parts: their motivation and contributions, high-level overview, indoor topology and roles, keyword organizations and relevance, search algorithms, as well as experimental studies. Let me first talk about the motivation. Recently, it is increasingly in demand in various indoor venues such as shopping malls, railway stations, and airports. Take the airport as an example. Suppose Jasper has just passed the security check for his flight to France and rode to the boarding gates in 1.5 hours. And during these 1.5 hours, he wants to buy some cookies, draw some cash, and eat a bowl of noodle. Then his need can be represented as an indoor routing query from a start point, say, security check, to a terminal point, say, his boarding gate. A desirable role should have a shop that sells cookies, an ATM or a bank that offers cash, and a restaurant offers noodles. The road should not be too long, which means the road distance should be less than the distance constraints. Our paper formulates the indoor top K keyword-aware routing query, device mapping structures to organize the indoor keywords and compute road keyword relevance. And it also derives pruning rules to reduce the search space in routing and conduct extensive experiments on both synthetic and real datasets to evaluate our proposal. The indoor top K keyword-aware routing query takes 5 parameters: the starting point PS, terminal point PT, distance constraint delta, a list of query keyword QW, as well as an integer K. Then it returns K rows from PS to PT, such that their row distance are within delta, and the ranking score are the best, or say the largest. And please let me first give you an overall idea about the architecture of the search algorithm very quickly. When we save the query, the search algorithm will initialize the priority queue to store all current row extension. We call them steps. And it will follow the find and connect paradigm. In each iteration, it fetches the step with the highest ranking score so far and expand it further using the function find with some pruning rules. And we use function connect to try to connect this newly constructed rows expansion that received from function find to destination and see whether some conditions are met. Prime check and prime update are functions for expansion, and we also have 5 pruning rules to increase the efficiency of the algorithm. Eventually, the top K result will be returned when the queue becomes empty. When we do indoor routing, we need to avoid the homogeneous rows. If 2 rows share the same head, tail, and a sequence of key partitions KP, we say they're homogeneous. Key partition KP consists of partitions that start point, terminal point locating, and those partitions that has keywords. So as we can see from this example, these 4 rows terminate at the partition V5, and V1, V2, V3 contains keyword, while V6 does not. So the KP of all these 4 rows are V1, 2, 3, and 5. So they're homogeneous rows. Assume we have a set of homogeneous row HR, then we say RI is a prime row if it is in HR, and it has the shortest row distance. And in our example, if R3 has the smallest distance, then we say R3 is prime row among these 4 rows. And besides, we also come up with 2 principles for indoor row search. The principle of regularity, to disqualify the row that contains 1 or more doors between two identical doors. And principle of diversity, to avoid the homogeneous rows in our indoor routing, which means we only keep the prime rows. Next, let's move to the queue organization and valence. We differentiate 2 types of keywords that are associated with indoor partitions. An identity word is to identify the specific name of a partition, like Starbucks, while a semantic word refers to a tag valent to that partition, like coffee and mocha. We can look at these mapping examples. As you can see, we can use P to I to map a partition to I words, which is many-to-one mapping, and I to P to map I word to partition, which is one-to-many mapping. We also have I to T and T to I to map between the I word and T words, which are both many-to-many mapping. And one thing I should mention is that for T to I mapping, we have direct matching I words and indirect matching I words. Then we can start to find the candidate I word set corresponding to each query keyword WQ. We denote it as kappa WQ. And each set entry is a pair of matching I words WI and similarity S, and all the S must be larger than a threshold tau. Kappa has 2 cases. If WQ is an I word, then the kappa WQ is itself with similarity equals to 1. Else if WQ is a T word, then kappa WQ consists of all direct matching I words WI prime, which comes from T to I mapping. For example, if WQ is coffee, then its direct matching I words are Costa and Starbucks, and that similarity equals to 1. Couple WQ also includes all the indirect matching I-words. The indirect matching I-words are retrieved from similarity calculation. And here we measure in the form of Jacquard similarity. It is like the portion of T-words that those two I-words shares. The larger the proportion, the more similar they are. If the proportion is larger than the total, we will include it into kappa. For example, when we consider WQ is lattice and an I-word coaster, we first use I2T to map coaster to its T-words, and we get coffee, drinks, mocha, and we denote it as ZA. Then we map lattice to its direct matching I-words, and for each of these direct matching I-words, WI, we get its related T-words. And we denote the union of these T-words as ZB. And then the similarity of each of these I-words and coaster can be computed using ZA and ZB. So we can start to calculate the keyword variance and the ranking score. The NQW of R is the number of query keywords that row R covers. Row is positive if here is at least one query keyword covered by R. In such a case, the left part of the summation indicates the number of query keywords that R covers. And the right part measures the average of each covered keyword WQ's maximum similarity score with its matching I-words on R. Then the ranking score of R is computed as a linear combination of normalized score of keyword variance and spatial variance as it is shown here. We come up with fine pruning rules for search algorithms. First, a partial row can be pruned if its distance plus the lower bound distance to destination is above the distance constraint. Although D can prune if the lower bound distance of the paths that going through the partition through this door is over distance constraints. And third, similar, a partition can be pruned if the lower bound distance of the paths going through this partition is over distance constraints. Fourth, given the current K's largest ranking score per side among the same complete rows, if the upper bound ranking score of a partial row is less than or equal to per side, then we can prune it. Last, a partial row R star can be pruned if it is primed by an obtained row R star prime. As I mentioned, we can use function find to expand the current partial row further. And there are two expansion strategies, topology-oriented expansion and keyword-oriented expansion. The idea of topology-oriented expansion is to reach all accessible doors from the current door based on the indoor topology. That is always expands from the current door to the next enterable door in the one hole. The idea of keyword-oriented expansion is to focus on the query words that have not been covered by the current stem and directly expand to one of those partitions that can cover some of those uncovered query keywords. Then the algorithm can be like this. First, we initialize a priority queue that used to control the order of row expansion. In line 2 and 3 obtain a set of all candidate I-words with reference to query keyword list QW and compute a set P of all key partitions that cover at least one keyword in QW. In line 4 to 6 are variables for pruning. They check the non-pruned door and pruned door. The row gives K's largest ranking score and a hash table for temporal prime rows respectively. Then we can start to pop elements in Q1 by 1 use function find to expand the popped row, get a set of valid stem ES, and use function connect to check whether it can be connected to destination directly. And when the queue is empty, we can return the case result, the top K results. And let's move to experimental studies. We do experiment studies on both synthetic and real data. We use this data to evaluate the TOE, KOE, and their variance. Specifically, TOE without D and KOE without D involves no pruning rules based on the distance constraint. And TOE without B, KOE without B skip the K-bound-based pruning rule. And TOE without P skip the prime-based pruning rules. But this variant does not apply to KOE because KOE is formulated based on prime rows. The KOE star uses the pre-computed shortest row between any two nodes. And here, we run each algorithm in the default setting and report the running time per query instance. For TOE without D and KOE without D, the distance-based pruning has greater impact on their efficiency. The KOE-based algorithm, like this, they fluctuate more on different query instances, while the TOE's expansion is relatively stable because they always find the next door according to indoor topology rather than the keyword list QW. We also evaluate the effect of integer k, the number of query keywords, the I-word fraction, beta, the floor number, the row distance, and so on. In general, KOE has better scalability when some distance-related parameters are enlarged. And conversely, TOE is more efficient when there are more query words. In addition, KOE always has a lower memory cost. And that's all for today's video. I'm very appreciating your watching and your time. Thank you very much.
Seems like there was a mild lag between the audio and the video. So does anybody have questions for Zijin?
Yes, hi.
Any questions? Again, I have the same question about scale. Can you say something about the scale? How does it scale with very large databases?
Okay. It really depends on the data size of the keywords and also the indoor topology. In our experiments, we have synthetic and real data sets, and they are the size of their I-words is around 1,000, and the size of T-words is about nearly 10,000. And in our default setting, the query time is around tens of milliseconds to 300 milliseconds. So it works well in our experimental data sets. So, but however, if we enlarge the data set to a very large size, it may suffer from a long query time. But however, because our problem is defined in indoor, so the indoor value usually not very large. So it means our solution works well in real scenarios.
Great. Thank you. That was a really nice talk. But yeah, that was a small. Yeah. So.
Yeah, I'm sorry, I'm not sure.
Oh, that's okay. I think Huan Lee seems to say that in this drive the video seems okay, so it could be just a lag in the play. But it was really nice, and thank you all to all the speakers And thank you for so many participants in this session. Thank you. So Kushagra and Anshul, looks like we are done with this session. Could you maybe stop the recording? And
yes.
Yeah.
Okay, thank you.